Today.
Right, you're the goat. Forever and always. I will.
Goat is the thing this year that I think I've heard more than anything else.
Yeah, you're for a long time. Wow.
Holy cow. You've reached a new level. Okay, different this year with geometry because it's shapes involved too, not necessarily just numbers and things like that. But first thing I want to know is, do you know what inductive reasoning is? Okay, so inductive reasoning is just reasoning based on patterns that you see. So basically it's saying, here's what I'm seeing happen. Here's what I expect will happen next. Okay, so we're just reasoning based on some patterns that we observe. So I'm going to start with a number pattern, and then we're going to move on to some shapes too. First example, I want to know what is the pattern and what are the next two terms. Okay, so if I give you, for our first one, this. Okay, dot, dot, dot just means we're going to keep going with it. So 3, 9, 27, 81. Can you tell me what the pattern is? Yes, Zaire. We are multiplying by 3. So 3 times 3 gets us 9. 9 times 3 gets us 27. 27 times 3 gets us 81. So our pattern, I'm just going to call it P for now, but I mean pattern. Our pattern is multiply by 3. Okay? So if that's our pattern, what are our next two terms? Right, you need to do 81 times 3, which would be 243. And then you take that 243 and multiply it by 3, and you get 729. Okay, so your patterns times 3, your next two terms are 243 and 729. Okay, questions on that? Okay, then how about this one? Let's see if we can just copy this. How do we copy it?
Oh, that circle with the square with the dots, right?
This one will copy it.
Oh.
Hey! Okay. So, if this is our setup, we have our first one, looks like this. Our second one looks like this. And the third one, sorry, I cannot draw straight lines in here, which is a polygon. So you're both right. You're both right. You're both right. All right, so if this is how it starts, I want to know the pattern and the next two terms. Now, you have to be pretty specific with this because you have to imagine if you were going to tell someone the pattern that's happening, they're not necessarily seeing the pictures. You need to be able to tell them, here's what's happening without having a visual of it. So be detailed, okay? Anyone want to try and be detailed with this? Remember, I love mistakes, so don't be bashful. Not that I'm saying you will make a mistake, but a lot of times people are less detailed than would be good here. Yeah, Allure. Okay, so the number of sides is being added by 1 for what? What else is part of this setup? In a circle, right? So we have a polygon inside of a circle, starting with a triangle where the number of sides increases by 1. Okay, something like that. So we'll just say within a circle, starting with a triangle, the number of sides increases by 1. Okay. So if we were to draw our next two terms, we would have a hexagon and a what? Not octagon. We would have a hexagon, so the next one's going to be 6,
I'm sorry.
right? So this is 6-sided. What's a 7-sided figure called? A what? A septagon is okay, or there's another name for it. A heptagon. So heptagon or septagon, they both work. So 1, 2, 3, 4, 5, 6, and 7. Okay? Questions on that? Okay. And I'll just warn you on quizzes and tests with this, so many times I say, give me the pattern, and then give me the next two terms. And for some reason, if it's a picture one, people only give me one. I don't know if it's just because a picture takes up more room, so they just feel like they're done, or what. But just be warned ahead of time. If I ask you for two terms and there's a picture involved, give me both of them, okay? All right, what's a conjecture? What? It's not a sneeze, no. A conjecture. I feel like you've probably talked conjecture in like a science class in the past, maybe? Or no?
It's a draw.
Is conjecture new to you?
No, it's a drawing.
Not a drawing.
Don't know.
Nothing?
It's a sketch.
You're all just afraid to tell me. I know you have an idea. It's a conjecture is basically like, it's kind of like an educated guess, right? I'm going to make a conjecture. I'm going to make this assumption based on information that I know. So it's not a wild guess, right? It's an educated guess. What?
Hypothesis.
Kind of like a hypothesis. Yes, a conjecture, a hypothesis. So what we're going to do is we're going to make a conjecture about this problem here. So we have example 2. Let's say we have 3 circles. I'm pretty stoked about this find here. All right, so in these circles, I want to know what conjecture you can make about the number of regions if there are 20 diameters. Okay, so I'm going to show you a couple different setups for this. So this first one, we're going to do 1 diameter. Okay, the second one, we're going to do 2 diameters.
Oh, I know what
And the third one, we're going to do 3 diameters. Oh, I didn't draw that very well, sorry. Oh. Okay, so in this setup, how many diameters in the first picture? There's 1 diameter. And how many different regions did that create? 2. That's great. Let me get us there. So there's 2 different regions, right? So 1 diameter has 2 regions, okay? How many diameters in the second circle? There's 2 diameters, and there are 4 regions. Okay, so 4 regions. The third one, 1, 2, 3, 4, 5, 6 regions. How many diameters is that? There's 3 diameters, and there are 6 regions, okay? The question is, what number of regions would we get if we drew in 20 diameters? Zaire. 40. How'd you get that?
You have to double it every time.
Right, we're doubling. So 20 diameters. If you look at the pattern here, 1 diameter gave us 2, 2 gave us 4, 3 gave us 6. So each time it was being doubled. The number of diameters times 2 equals the number of regions. So if we multiply this by 2, our conjecture is that there would be 40 regions if we had 20 diameters. Okay? That's not to say that's absolute truth. It's a conjecture. It's what we're assuming will happen based on the pattern that we're seeing. Okay? So that is making a conjecture. Any questions on that? Okay. When you make conjectures like this, you need to make sure that you gather enough data to make sure that our conjecture makes sense. So we're going to do another problem. This is example 3. And for this one, we want to know, what do you think the sum of the first 30 even numbers would be? Okay, the sum of the first 30 even numbers. Now, this one, it would be to your best interest if you make a chart just to compare, because the more you have, the better it is. So we're going to talk about the number of terms, how many even numbers we have, and their sum, and we're going to set it up so that we do a few of these. Okay, so if I have one even number, what's the sum? It's not technically a sum. 2, right? Your first even number is 2. Okay, what if I have 2 even numbers? What's the sum of the first 2 even numbers? 6. You would do 2 plus 4, so 6. Okay. The first 3 even numbers would be 2 plus 4 plus 6, which would be 12 plus 2. And then the first 4 even numbers would be 2 plus 4 plus 6 plus 8, which would be 20. Okay? Now, here's the deal. This one's not...
Number to the next number. Yeah.
Right. But if I want to get to 30 even numbers, and I do it that way, I have to go 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 8, and I'm only at 10 right now, right? You got to do that 30 times. That's going to take you a little while and be a little bit obnoxious. So it's better to look for a pattern, something going on that we can make a conjecture about. So if you look at your sums, this was 2, 6, 12, and 20. You've got to look for how that relates to our number of terms. Karen, did you have your hand up? No? Changed your mind? Maddie.
Each time that you have a new sum, it adds, so like 1 times 2 is 2, 2 times 3 is 6, 3 times 4, so it goes up by 1. I don't really know how to explain.
Yes, you're right. So one term, right? If I multiply it, oh, I'm still on my highlighter. If I multiply that 1 times the term right after it, right? 1 times 2 gives us 2. If I take my 2 and multiply it by 3, 2 times 3 gets me 6, okay? My 3, if I do 3 times 4, I get 12. And then for my 4, I do 4 times 5, and I get 20. Okay, I know this is not the easiest one for all people to see, so I get it if you don't see that right off the bat. But it's always going to be the number times the number of terms right after it. So if I'm looking for the first 30 even numbers, what multiplication problem am I doing? 30 times 31. So you would do 30 times 31, and you get 930 as a conjecture for what we think the first 30 even numbers sum would be. Okay? Questions on that?
Nah, it's pretty straightforward.
Good. Okay, so now here's the thing. Not all conjectures are true. you're going to come up with some that aren't actually going to work. What we can do to find out if that's the case is look for counterexamples. Remember yesterday we talked about counterexamples a little bit. A counterexample is just something that's going to prove your statement, your statement false. So we're looking for a counterexample. So I'm going to give you a few problems and see if you can come up with what counterexample would prove it false. Okay? And we're skipping example 4. I'm going on to example 5 here. All right, if I make this statement, if the name of a month, what are you doing? I don't either. Stop. If the name of a month starts with J, then it's a summer month. Okay, so here's the deal. A counterexample means the hypothesis is true, but the conclusion is false. What's our hypothesis right now? The name of the month starts with J. So we want that to be true. We want a month that starts with J, but we want this part to be false. So what is our counterexample? January. Okay, that would be our counterexample. How about this one? You can connect any 3 points to make a triangle. Can you give me a counterexample to that? And if you need to see it as an if-then, you can turn it into an if-then, right? So if you connect any 3 points, then you can make a triangle. If that helps you to hear it a little better, see it a little better. What would a counterexample be? A straight line. So if I have 1, 2, 3 points connected, it doesn't make a triangle, right? But it is a counterexample to what we have in letter B there. Okay. Last one. What if we said, when you multiply a number by 2, the product is greater than the original. Okay, when you multiply a number by 2, the product is greater than the original. Can you find a counterexample to that statement? Yeah, Sam.
0.
0. Okay, so when you multiply 0 by 2, your product is not greater than what you started with, right? 0 is not greater than 0. Okay, so 0 would be a counterexample. Anyone else have another counterexample? -2, right? Any negative number would work. So you could say 0, or you could say -2, because -2 times 2 is -4, and -4 is smaller than -2. Okay, so a negative number or 0 would be your counterexample. Questions on that? Oh my word.
It's
It's most definitely
So giggly.